Okay, hello everyone. Welcome back. Due to popular demand, we are back with more videos. Today we're going to start looking at data structures and algorithms, the famous DSA, right? We're going to start looking at data structures and algorithms because, yeah, it seems you guys want them, so we've come to deliver. Now, I already did the introductory video, of course, a couple, I think that was a month or two ago. So go back and watch that. Also, on my YouTube channel, well, if you paid for the tutorials as you're on the YouTube channel, you're actually going to find videos on algorithms. So I do recommend you go back and revisit basic algorithms from last year in second year, because they are going to help you out a lot with what we're doing here. But yeah, assuming you've watched the videos for algorithms now, okay, now we can start the actual meat. Algorithm analysis, right? Algorithm analysis. Algo analysis. However you spell it anyway. So algorithm analysis, basically we're just going to be analyzing some algorithms, right? We're going to be talking about the famous runtime complexity, big O of n, you have small O of n, and some other funny symbols like whatever this symbol is. Anyway, yeah, so we're going to be discussing that here. And to start off with, we're going to just do a few definitions, right? A few definitions. Again, it's going to be similar to last year's video as well. We're going to go straight into the solving, but just like a small preliminary video, just to get us excited with what we're about to start doing. Okay, so first things first. T of n. T of n is equal to big O of f of n, right? Big O of f of n, right? Big O, basically, when you just hear big O, they're basically talking about, okay, what's the worst case scenario, right? What's the highest amount of time it will take um this function to run, right? So this time is usually less than or equal to the actual big O. So big O notation is just the uppercase, in short. That's how I've always considered it, and but for the definition here, it's basically if there is a positive constant, right? If there is a positive constant c and n naught, right? If there's a positive constant c and n naught, then t of n is less than or equal to c f of n. Remember this definition. Remember this definition. We're going to use it for a lot. This one right here can get you a lot of marks. Just this definition. We're going to solve a lot of questions with it. The other one is definition 2 is t n. Not sure if this symbol is omega or whatever. Those of you who've played God of War, you know this symbol. For me, I know it from Ohm's law resistors. But yeah, this one is basically the same thing, only that t of n is going to be greater than or equal to c g of n, right? So same thing, almost the same thing as the previous one, only that this time now, this guy over here is smaller as compared to here where the runtime was actually higher, g of n. Okay, and then the final one, again, what they call this symbol, but it looks like theta, but this one is going to be with like a thing in there, and then h of n. Yeah, whatever you call this symbol. Those of you who know what this symbol is, please tell me. Yeah. Otherwise, it's going to be Tn is equal to basically basically what this is if and t of n is equal to this if and only if Tn of big O of h of n, right? So if this h of n is equal to this and it's also equal to this, right? So if it's equal to this and equal to this, then this one stands valid. Okay, then finally we also have small o of n, so we have big O and then small o of n, which is if all positive constant c, right? If for all positive constant c there exists n naught such that t, right, such that t of n is less than c p of n, right? Tp of n when n is greater than n naught, less formally, t of n is equal to small o pn if tn is equal to big O of n and tn is not equal to this one over here. Yeah, you can use Maclaurin West for those definitions really. But then other things that we really need to know for this one is, first of all, growth of a function, right? Because this is one thing that you're going to be looking at a lot. What is the growth of a function? When you okay, which function grows faster than this, etc., etc. So basically, if I draw a very simple graph here just to demonstrate what I'm trying to talk about, a very simple curve there. So basically, functions do what we call grow, right? Functions do what we call grow, and basically growing is how much time, right? How much time going in this direction. It's basically a graph of time versus the number of inputs in, right? So when a function grows, we're basically saying as we increase the number of inputs, right? As we increase the sample size, right? The number of things that this function has to do, how much time is it taking for it to complete? This is linear time, so this is n, right? This is linear, right? This is the linear curve, so this is n, right? Which is basically just O of n. And then you have things called constants. So constant time is basically, okay, no matter how big n gets, this will always stay the same, right? So this is constant. This is in big O notation. So in big O notation, this is O of n, and then this other guy here is O of 1, because no matter how big it gets, it will always stay constant. And then you have others such as quadratic time, right? You have others such as quadratic time where they start off properly, but then they branch off. They start off quite well, and then they just, yeah. So we all know quadratic functions. You have logarithmic functions that grow rather slowly, right? You have so this is maybe something like O of n squared, right? Then you have curves that logarithmic, right? So you can have something like um, you can have something like logarithmic functions that grow very slowly actually. Then you can have exponential functions that grow, well, exponentially. So a small increase in n basically means a very, 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 very large increase in the rate, right? So meaning functions that grow fast are actually slower. So basically when you start doing asymptotic analysis, asymptotic analysis, yeah, we are actually going to explore these more, but for now just note, okay, different functions grow at different rates, right, based on these guys. And then there's actually an order to them, right? There's actually an order to them that again I recommend you try to understand, right? That you should try to understand. But roughly, let me just pull up my notes here so that I don't start lying to you guys. Yeah. um, where are these things? Yeah. So roughly these guys have an order in which they grow, right? They just don't pop out of nowhere. So a simple one is constant time, right? Constant time, and this is from fastest to slowest, or those that grow the slowest to those that grow the fastest, right? So basically it increases in this direction, right? It will increase in this direction, and we start off with, first of all, constant time, right? Then you can have logarithmic functions. You can have logarithmic functions there, and then you can have log squared. So log to the power 2 of n. This one, I found out that it's actually just a log n squared. Yeah, I don't know, it would always mess me up, but this is actually what it just means. Then you have stuff like n, right? This is linear time. Then you have n log n, right? N log n. Then you're going to have like your n squared there, n to the power 3, and then now you have, so these are like your quadratic, cubic, and then finally now you have your exponentials. These are big. When you're programming, you don't want code that looks like this. And again, there are functions that would, there are times where we're going to talk about, well, okay, if something is inefficient, the moment you just see something like this, I just know you're too inefficient, and in most cases you're repeating work. Yeah, this video is getting long enough anyway. But yeah, so we have those simple ones, and let me just do a few more rules before we actually get into solving, because I personally don't like a lot of the theory. The theory is important, yeah, you have to understand it, but I don't like teaching it out because you can just read that on your own for the most part. Yeah, just there for explanations. There are a few important things we need to know. First of all, First of all, if we have T1 of n, right, T1 of n being equal to big O f of n, right, f of n, we have that there, and T2 of n being equal to big O g of n, then one, we can add these, right, we can add these. We can basically say T1 of n plus T2 of n. This is going to be O max f of n plus g of n. I'll explain what this is in a moment because it's actually a very important concept that we're going to be using throughout. Then we're going to have T1 of n times T2 of n. This is basically equal to O f of n times g of n, right? Okay, so it's just a simple rule that you should always remember, right? And then if n is a polynomial of degree k, okay. But then, what is this over here, right? Basically, right? Basically, when you have a function, let's say our function f of n is equal to, off the top of my head, 3x 3n to the power 3 plus 2, okay, 2n plus 7n there plus 1. What is going to be the order of this function? What is going to be the big O notation of this function? The big O notation of this function is basically the highest order, right? Which one of here has the highest order? Of course, it's going to be n to the power 3. So this is of order n to the power 3, right? Because this is the largest thing that we have over here. And again, this will become more apparent as we actually start doing the questions in the next video. But just remember this, right? When you have a function like this, right, the order is going to be the biggest one here, which is why, going back to this one, the way this one was presented, if we have something like f of n, right, f of n being equal to 3n plus 1, and then g of n being equal to 2n squared plus 2. Of course, the order of this, if we add these two, the order is going to be the larger one, right? Which one has the largest one? But then, when you multiply them, basically what you're doing is you're going to get the product of this and this, and I'm assuming from I in it, the biggest term there will be 6n to the power 3. So the order, if we were to multiply these two guys, it would be O of n to the power 3, like that. So just a few things to remember. Again, we'll start solving. Don't worry, the next video I'm actually doing a question, so yeah, we're going to apply what we learned here, but 13 minutes is already long enough. Peace for now.